Okay, for this video, I'll be going through pure physics electromagnetic induction tutorial. Okay, question 1. Wire ABC connected to a center zero galvanometer. That means when there is no reading of current, when there's no current, okay, no current, the galvanometer will point to center zero. So if let's say now there is a current going from left to right, example. Okay, so that's why it is connected in series. When current is going from left to right, the galvanometer will be deflected to the right. Okay, and if now the current is going in the other direction from right to left, okay, then the galvanometer will be deflected to the left. So when there's no current, the galvanometer will be at center zero. So the wire is placed between the poles of two magnets. So I see that there is a north and south given, and magnetic field of this external magnet goes from north to south. Okay, so now when the wire is moving downwards, we are giving a force, so the motion is downwards. The galvanometer needle deflects to the right as shown. That means current is flowing in this direction. Okay, so on the diagram, draw the direction of the induced current. It is from C to A. Okay, so this is from your understanding of the deflection of the galvanometer. Now, is there any force which opposes the motion of the wire? Yes. If yes, that is origin. Okay, so the answer is yes. The induced EMF, right, and current will produce a magnetic field that opposes the change producing it. So this is actually Lenz's law. But first, maybe we explain why is there an induced EMF. Okay. So this is in accordance to Faraday's law. So if I were to look at the wire in this direction, okay, from this perspective, so I will see my north on the left and I see my south pole on the right. This is for the external magnet. Okay, and the magnetic field goes from left to right. And now I have my wire. Instead of seeing the whole length, I see the cross section of it. Okay, and I know that the force is going downwards. Okay, so this is electromagnetic induction. We are actually providing a force for the wire to cut through the magnetic fields. Okay, so we are providing a force for the wire or the conductor to cut through the magnetic field. So since you are providing a force and we get an induced current, okay, we get induced current, we are actually like generating a current. So this is generator, and if it's generator, we need to use Fleming right hand rule, where the thumb represents the force, the middle finger represents the current, and the first finger represents the direction of external magnetic field. Okay, but the question already tells us what's the direction of the current if you know how the galvanometer works. But let's practice using our Fleming right hand. So you need to have your thumb pointing downwards to the bottom of the screen, and the external magnetic field, which is your first finger, pointing from left to right. Okay, so if you are like me doing the Fleming right hand rule now, your middle finger will be pointing to yourself, and it's quite an awkward position. Okay, but I'm still managing to get it, and I'll get my current coming out of the screen. Okay, so this is what you need to know. So why is there an EMF? Why is there an induced EMF and therefore an induced current? It's because as the conductor or as the wire is cutting through the magnetic flux of the external magnet, there'll be a rate of change of magnetic flux linking the conductor. Okay, so we can think of it as the external magnetic field is like that. So if we go down, it cuts through a magnetic field Then over here it doesn't touch any magnetic field, right? This model, and then continue to cut and no cutting, and it cuts again. So there's a constant rate of change of magnetic flux linking the conductor. So according to Faraday's law, there will then be a induced EMF, and because it is a complete circuit, right? There's a complete circuit, therefore there will be an induced current. Okay. So this is to explain why is there an induced EMF and therefore an induced current. Okay. But now there is a supposedly opposing force, okay, which is stated by Lenz's law. Okay. Why is that so? Because as your induced current flow, we learned in the previous chapter, electromagnetism, okay, when there is a current, when there's a current flowing, okay, it will produce a magnetic field, produce a magnetic field of its own. Okay, and because it is actually in a magnetic field of an external magnet, so I bring this over, right, and this is the wire, and now I'm drawing in the dot, which is actually the induced current. So for this induced current, okay, it will produce its own magnetic field. So now I'm going to use my right hand grip rule with the thumb pointing in the direction of the current, and therefore I will have a magnetic field that is in the anti-clockwise direction, And if I were to draw in my external magnetic field, right, and if I were to look at the top, the black and the blue arrow actually are in opposite directions, so they will cancel each other out. So there is no magnetic field. And if I were to look at the bottom of it, they are in the same direction, so it is reinforcing. So it goes from 2 to 0, which is the magnetic force. And therefore, the interaction of the magnetic fields, the two magnetic fields, one is by the external magnet, the other one is by the induced current. Okay, the interaction of the two magnetic fields will produce a magnetic force, and it goes from more magnetic field to less magnetic field, so it is going upwards. So this is the force that actually opposes the change producing it. So you must remember, when we push this wire down, the motion is downwards. Okay, but when we push down this wire, there's a rate of change of magnetic flux linking the wire. According to Faraday's law, there will be an induced EMF and therefore induced current. Now that the induced current is flowing, it will produce its own magnetic field. Okay, it will produce its own magnetic field, and this magnetic field will then interact with the external magnetic field, okay, to produce a magnetic force. And the direction of the magnetic force is opposite to the motion of the wire. So this is Lenz's law. To the direction of the induced current will flow in a direction so that the magnetic field it produces will interact with external magnetic field to produce a force that opposes the change producing it. Okay, so actually there's a connection between the previous chapter of electromagnetism and electromagnetic induction. Okay, so let's look at the actual answer. How can we write it? Okay, so is there any force? Yes, there is a force because the induced current, okay, will produce a magnetic field, okay, that opposes the change producing it. So this is Lenz's law, right? And in order to understand how the force is produced, you need to look at the magnetic field and the external magnetic field, how they interact. Okay, so the magnetic field produced by the induced current in the wire will combine with the permanent magnetic field and produce a force upwards. Okay, the bottom we have magnetic field in the same direction. The top their interaction is cancel each other out, so it's from stronger to weaker field region. Okay, now to which side will the galvanometer needle deflect if the wire is moving upwards? Therefore, it will be in the opposite direction. The galvanometer will deflect to the left. Okay, because the direction of the motion of the wire is changed. Moving in a positive x direction. Where's the positive x direction? It is to the right. So if it's to the right, right? So now imagine I draw my external magnetic field. My conductor or my wire is also going to the right. So there's no cutting of magnetic field lines. There's no rate of change of magnetic flux linking the coil, right? So even if I go from left to right, okay, there is no cutting of magnetic field lines. So therefore, there is no deflection, okay, or the galvanometer will go back to center zero. Okay, why is that so? Because the motion is parallel to the field, therefore no cutting of magnetic field lines or no change in magnetic flux linking the wire. So this is how you write down your explanation. How about moving in a positive y direction? Okay, so what is the y direction? Let's take a look. The y direction is actually into the page, So this is the z direction. So this is how we represent 3D. Okay, so y is actually going into the page, or if I want to do a 3D to 2D, so this is z, this is x, right? So y will be into the page. Okay, sorry, it should not be a dot, it should be a cross because it's going into the page. Okay, so cross means going away from you. So again, there is no deflection, so like this, because there's no change in magnetic flux linking the wire. Okay, explain how and why would the induced current change if the separation between the two magnets is reduced. So that means the magnetic poles are coming closer together, so there will be a stronger magnetic field strength. Okay, will become stronger, and it will then lead to a greater change in magnetic flux linking the wire. Okay, so therefore a larger induced EMF according to Faraday's law. Okay, it is directly proportional to the rate of change. So therefore there will be a larger induced current. That means the galvanometer will actually deflect to the left or to the right with a larger magnitude. What happens if the wire is moved downwards faster? So there will be a larger rate of change of magnetic flux. Then according to Faraday's law, there will be a larger induced EMF and therefore larger induced current. Now what happens if the wire ABC is folded and moved downwards? Induced EMF in BA and BC will oppose and cancel each other out. Okay, so if you want, I can draw it for you. This is north, this is south. Okay, and this is the wires. So this is AB portion, this is BC portion. So if I were to move both down, right? Okay, so this is the force on AB, force on BC by us, and then you apply your Fleming right hand. Okay, so the current will be flowing out of the page for AB and also out of the page for BC. That means the current will be flowing this way, current will be flowing this way. And because they will cancel each other out, therefore the galvanometer will remain at center. Okay, question 2, it shows two solenoids wound on a paper cylinder. Okay, take note, even if it is an iron bar, okay, the current do not flow in the iron bar, they always flow in the in the wires. Okay, so explain what happens to the bulb at the instance where key K is closed. So you need to know this step. So over here is positive, the long side, and this is negative. Once the switch is closed, current will come out from positive, and you need to draw all these wires, the current in this solenoid, and then you apply. So this is first step, this is second step, and third step is you apply your right hand grip rule for solenoid, okay, where the thumb represents the north. So now if I drew the wires, it will help me to identify that over here is a north pole and over here is a south pole. Okay, so initially there wasn't any south pole on the secondary coil. Let's call this a secondary coil. Okay, initially there wasn't this when the switch is open. So now suddenly a south pole appear, and then according to Faraday's law, okay, it experiences a change in magnetic flux, right? The secondary coil experiences a change in magnetic flux. So a salve appears, and according to Lenz's law, so the current flow in the secondary coil must flow in such a direction so as to oppose the change producing it. So in order to oppose the change, here must also be a salve, because salve appears, okay, and it wants to oppose it, so over here must be a salve. Therefore here will be a north. And then if this happens, again you apply Fleming. So this is Lenz's law, this is number 2, south pole, and then you apply right hand grip rule for solenoid. Step 3, right hand grip rule for solenoid. Okay, you can then use your thumb to point to the right, and then the current will be flowing in this direction. Okay, so the current is actually flowing in this direction, and therefore the light bulbs light up. Okay, so the light bulb will light up momentarily. So this is important. Later I'll explain why. We finish first. At the instant K is closed, when K is closed, there is a magnetic field produced, okay, by the left solenoid, and this results in an increase in magnetic flux linking the right solenoid, or it experiences a changing magnetic field, okay, a change in magnetic field from don't have to have. Okay, and by Faraday's law, it will induce an EMF and therefore an induced current. Why is it momentarily? Because after that, okay, the current on primary coil remains constant. So there will be a magnetic field produced. Okay, a constant magnetic field will be produced. Right, so for the secondary coil, there is no change or rate of change of magnetic field. Right, there's no more, because it is a constant magnetic field. Therefore, according to Faraday's law, there will be no induced EMF and therefore no induced current. So this is actually to explain this part. What happens if key K remains closed? The bulb remains unlit. As K remains closed, magnetic field produced by the left solenoid remains constant. There's no change in magnetic flux linking the right coil. So by Faraday's law, no induced EMF. What happens when the switch K is open? The bulb lights up momentarily again, right? Because as the magnetic field disappears, the magnetic flux linking to the right solenoid decreases, and by Faraday's law, induces an EMF and hence an induced current. Okay, so what happens when the salve is gone? Okay, so the salve is gone, becomes 0, because initially when the current is flowing in this DC circuit, there will always be a salve, but now when I turn off the switch, the salve will disappear. So in order to oppose this change, in order to oppose the salve going away, the right solenoid will now produces a north pole due to the induced current. The current will flow in such a way, the induced current will flow in such a way, so that it will produce a north pole to oppose this change of salve moving away. So then the current will switch direction. So if I were to replace this with a galvanometer, it will swing to the left, go back to 0, swing to the right, go back to 0, something like that. Okay, so there will be a change in direction, and this is your alternating current. So what you observe if K is closed and open at a frequency of 2 Hz, so the bulb will flash at a frequency of 4 Hz. There will be 2 cycles of close and open. Now suggest 2 ways to increase the brightness of the light bulb. More turns in the coil, very important, not more coils. Okay, so more turns in the coil on the left or on the right. Use a stronger battery for the left circuit so that there will be a stronger current on the left, so that there will be a stronger magnetic field produced. Okay, or we can use a soft iron core. The purpose is to concentrate the magnetic field lines produced by the left coil magnetic field. Okay. Okay, then question 3, in the diagram below, P and Q are two coils of insulated wire. Coil P being connected to a 36 watt, so this is my P, 12 volt battery, 12 volt lamp, so this is my V. Okay, so it's observed that the lamp was light when an alternating current supply is connected to Q, but not when a direct current. Okay, you see that there's actually no connection between both. Okay, they are just in close proximity. Okay, so this is the supply, and now we have AC. So what happens when we have AC? We have alternating current. Current changes direction. Okay, and when current flow, it will produce a magnetic field. So it will produce a changing magnetic field. So it could be a north and south, and then the next moment become a south and north. That is produced in coil Q. Okay. Now coil P will then experience a rate of change of magnetic flux. Right? Before that it was north and south. Then after that it changed to south to north, and then it will experience north and south, south to north again. So there will be a rate of change of magnetic flux linking coil P. So then according to Faraday's law, there will be an induced EMF. Okay, and hence an induced current. And therefore the lamp will light up. Okay, so account for the observations described above. With an AC supply, the current changes direction periodically. This produces a continuously changing magnetic field around coil Q. So magnetic flux linking coil P will change, and by Faraday's law, please quote the law, it will induce an induced EMF and a current. So the light bulb lights up. So if it is more than 2 marks, you need to talk about why not DC, because it was mentioned that when the supply is DC, the lamp doesn't light up. So with a DC supply, the magnetic field produced around coil Q remains constant. So this is like your previous question, question 2. There is no change in magnetic flux linking coil P. Okay, therefore by Faraday's law, no induced EMF. Now with the alternating current supply connected to Q, why will the brightness of the lamp decrease if P is moved away? So the further away, the weaker the magnetic field due to Q, right? So then this reduces or decreases the rate of change of magnetic flux linking coil P. So according to Faraday's law, induced EMF is smaller. So Faraday's law is actually the rate of change of magnetic flux. Okay, so there must be a change, and the size or the magnitude of the induced EMF and induced current actually depends on this rate of change. So the larger the rate of change, the larger the induced EMF. Okay, with the alternating supply connected to Q, an aluminum rod held along the axis through the center of P and Q becomes warm, but a plastic rod does not. Suggest a reason for this. So if I use an aluminum rod, right, the change in magnetic flux linking the aluminum rod, because it's a conductor, okay, induces an EMF and current since it's an electrical conductor. So this causes the rod to heat up. But on the other hand, no EMF and current will be induced because plastic is not an electrical conductor. Therefore, it will not heat up. Okay, question 4. What's an anemometer? It's a device for measuring wind speed. So, describe how the anemometer works. Okay, so you must imagine, let's say now there's a wind blowing. So it will then turn all these rubber cups. And these rubber cups, the axis is linked to this magnet. So this magnet will turn as well. So when it turns, the coil of wire that is positioned at the bottom will experience a rate of change of magnetic flux. Because right now, north is here, south is here. But once it turns half a revolution, then it will be south and north, right? It will then be south and north, okay? And if the wind speed is faster, there will be a larger rate of change. If the wind speed is lower, then there will be a lower rate of change of magnetic flux linking this coil wire, and then therefore the voltmeter which measures the induced EMF will register a higher or lower reading according to how the rate of change of magnetic flux is. Okay, so let's see how to write the answer. The wind applies a force causing it to turn, right? So this causes the magnet to turn as well, and the magnetic flux linking the coil of the wire will therefore change. So this is according to Faraday's law. It will induce an induced EMF in the coil. Then when the wind speed varies, the speed at which the magnet rotates also vary. So it affects the rate of change of magnetic flux. So this term keeps coming up, or rather this whole phrase keeps coming up. The rate of change of magnetic flux linking the coil. So it's a good idea to know how to incorporate this into your answer. And therefore the induced EMF changes with the wind speed. Okay, so suggest two ways to improve the sensitivity. Okay, so increase the surface area of the rubber cup, then it will capture more wind, right? And it is then able to measure the wind speed more accurately. Add more cups as well. Now increase the number of turns of the coil, use a strong magnet, and use a more sensitive voltmeter. Okay, I actually saw an answer in some of the scripts that you handed in. Okay, so that answer is not allowed because they are asking for the sensitivity. Okay, so I forgot what the answer was, the wrong answer. Maybe some of you can actually let me know what is it, then we can share with everyone. Okay, question 5, it shows an ideal transformer. So that means PP is equals to PS. With 200 turns in the primary coil, so I can do NP equals 200. 400 turns in the secondary coil, so NS equals to 400. So since the number of number of turns in secondary is more than primary, therefore this is a step-up transformer. Okay, so a short-lived current, that means very momentary, will be induced in the secondary coil at the instant the switch is closed. Why? Because this is positive, this is negative, current flows here, right? So this is step 1, this is step 2, you have to draw this current, and then step 3 is to apply your right hand grip rule for solenoid, and your north is here, step 4, and then Lenz's law, step 5, it will be a north here, Lenz's law. Okay, so what's the direction of the current? Again, then you apply your right hand grip rule. Okay, and you know that the current will be flowing in this direction, so it will going from A to B. Okay, so these are generally the steps. We have seen this in the previous questions, right? So you need to know what is the direction of the current flow in the solenoid, very important. Then you apply your right hand grip rule so that you can get the magnetic field that is being produced, where is the north and where's the south. And then if you are talking about Lenz's law, then you can apply it to the secondary coil. So explain why transformers can be used only with AC supply. So AC produces a changing current in the primary coil, therefore it produces a changing magnetic field, and this allows for continuous change in magnetic flux linking the secondary coil, and then by Faraday's law, an EMF that alternates continuously can be induced. Okay, please take note that by right, the current that's over here will not flow in the iron core. Okay, it is the magnetic field lines that is in the iron core. Okay, now the primary coil is connected to a 10 volt AC source, 10 volt AC source. So this is the VP. VP equals to 10V, and the input waveform is shown. Okay, so it goes from 10 to minus 10. Okay, so what's the voltage across the secondary coil? So you need to apply this formula, turns ratio NP over NS equals to VP over VS. Okay, yeah. Oh, I think it's the turns ratio is the other way around. NS over MP okay, equals to Vs over Vp. Okay, so anyway, you apply, we have Ns, which is 200. Sorry, I think it's 400. Okay, MP is 200, VP is 10, so this must be 20. So what's the frequency of the current in the secondary coil? It will follow what is the frequency in the primary coil. So this is our voltage versus time. So the time taken to complete one wave is actually 0.05. So that is the sort of period, which is 0.05, and frequency equals to 1 over t, so equals to 1 over 0.05, and you will get 20 hertz. Okay, now the galvanometer is replaced by a resistor of resistance of 100 ohm. What's the current in the secondary coil? So just now we calculated our Vs to be 20 volts. So using V equals to IR, you will get 0.20A. So this is my Is. Okay, and because it's ideal, we can actually calculate the IP, calculate the current in the primary coil, which is IP. Okay, so how do we get this formula? Very simple. If it's ideal, it is PP equals to PS. So IP VP equals to IS VS. Then you substitute in, you'll get 0.40 ampere. Okay. Now explain why in practice efficiency is always less than 100%. So you need to memorize these few factors. There will be power loss due to resistance in the coil or wire. Okay, so this is P equals to I square R. So this one is also in your transmission cable. And then the flux leakage between the primary and secondary coil. So even though we use an iron core, right, to concentrate the magnetic field lines, but there will still be some flux leakage. That means some of the magnetic field lines will not be completely linked to the secondary coil. Or there will be an induced eddy current in the iron core, and then this leads to energy transferred to the internal store by heating. So we actually have a transformer in your laptop charger, so that's why sometimes you touch it after a long period of use, there will be you feel that this thing becomes hot. Okay. Now suggest two ways to improve the efficiency. So use low resistance wire. So this is for transformer, so we are just talking about transformer. So we use a low resistance wire by increasing the cross-sectional area of the wire, or we use a laminated core. Okay. Now a transformer has 20,000 turns on the primary coil. So what I do is I will write NP equals to 20,000, 400 turns on the secondary coil, so NS equals to 400. So because this is larger, therefore it's a step down. Okay, so the efficiency of the transformer is 100. That means this is ideal. Okay, that means PP equals to PS. Determine the output of the transformer when the input is an alternating supply of 240 volts 50 hertz. So if this is 240 volts, this is my VP, right? VP. So you use the turns ratio formula, Vs over Vp equals Ns over MP. This is very important, so you need to annotate, write down all this information. Okay, so Ns is 400, correct? This is MP, and this is my VP. So you should get 4.8 volts and 50 hertz. Now the transformer is used to operate a 9.6 watt lamp. So this is the power from the 240 volt supply. 240 volt supply, this is from the VP, right? Okay, but the Vs is 4.8 volts. So calculate the current in the secondary coil. So using P equals to IV, and now we need to make sure that our values is correct. They want the current in the secondary coil, so this is IS, and over here I should be using VS. So I need to substitute 4.8, so I get my IS to be 2 ampere. So what's the current in the primary coil? So since PP equals to PS, right? PP is made out of IP, and VP equals to ISVS. Okay, so I have my PS to be 9.6 watts, correct? 9.6 watt, this is what I have. IP was what I need to find, VP was 240. Okay, so IP equals to 9.6 over 240. So you should get this answer. Okay, that's why for transformer, very important to annotate and make sure that you're talking about the primary side or the secondary side. Okay, question 7. Remote village is supplied with electricity from a power station some distance away by power cables. At the village, the transformer steps down. So this is a step down. Okay, where your NS is lesser than NP. And your Vs is lesser than Vp. So this is the primary side. This is the secondary side. R represents the net resistance of the electric circuit in a village. The mean power supply is 500 kilowatts. That means this is 500 kilowatts. Oh, may not be the mean power supply to the village. So it could be 500 kilowatts here. Okay, let's read on. Explain why a high voltage of 10,000 volts is used. So this is my VP. Okay, so this is my Vs for this side. When transmitting using a high voltage, that means over here, there is also a transformer. It is a step up. Step up. Okay, so the Vs here, okay, and the Vp, because this is step up, I need to step up the voltage so that the transmission current can be low. Okay, because power equals to IV. If my voltage is high, therefore my current will be low. Why do I want a low transmission current? Because when we transmit using a high voltage, we will have a low transmission current. Having a low current will reduce power loss. Quote this formula: power loss equals to I square R. So in the form of energy transferred by heating to the internal store of the cable. Therefore, this power loss, okay, which is energy that's being transferred to the cable, will be very low. Alright, so I don't lose any power during this transmission process. Now, the power cables used are usually quite thick. Explain the reason for doing so. So if it's thick, right, that means there's a large cross-sectional area, large A. And because R equals to rho L over A, if I have very thick wires, my cross-sectional area is large, so therefore the resistance of the cable will be low, right? Because the length, imagine it goes from the power station all the way to the village, many kms away, the length will be very long, right? So I can try to reduce the resistance of the wire by having a thicker wire. So a large amount of energy will be transferred by heating to the internal store with high current. To prevent overheating, reduce power loss, thick wires are used as they have low resistance. Okay. Now calculate the current flowing in the secondary coil of the transformer. So far what do we have? We have, if we are focusing on this side of the circuit, Vp equals 10,000 volts. We don't have NP, okay. We have Vs to be 250 volts, and I can take this power PS to be 500,000 watts. Okay, so with this I can actually find my IS. So IS is 2000 ampere. Okay, right? And then because they ask us to assume that transformer is 100% ideal, so PP equals to PS. And PP is made up of IP and VP equals to 500,000 watts. And since I have VP to be 10,000 volts, therefore IP will be 50 ampere. Okay. So if the power cable has a resistance of 20 ohm, calculate the power wasted in the cable. That means the power loss due to I square R. Okay, so I square R, we just calculated that the transmission current is 50 ampere. Okay, and the resistance is 20 ohm, so therefore the power loss is 50,000 watts. Okay, therefore the power must draw from the power station will be in addition to the 500,000 watts to give us the 550,000 watts. Okay, so this kind of question is quite typical in O level. Now, figure 8.1 shows a Christmas lighting containing 60 miniature bulbs, each rated at 2 watts. So this is the power of each, and 5 volts. Only 2 of these bulbs are shown. Okay, so this is main supply of 220 volts. And we know that this is a transformer. Okay, so this is the primary side. So in O level, the left hand side is always primary, the right hand side is secondary. So from this, I know Vp equals to 220 volts. Okay, I know Np equals to N1 turns. Okay, on the other side, if for secondary, I know Vs equals to 5 volts. So I know N2, number of turns in secondary equals to N2. Okay. Now, to operate the lighting set normally, it's found that a transformer is needed. Calculate the turns ratio. Okay, the turns ratio is NP over NS. Okay, so this one we need to take note. Just now I think I may have said it correctly and then I switch. So it is NP over NS. So we can actually get it from the ratio of VP over VS. Okay. So Vp over Vs will be 220 over 5. So this is 44. So this is the turns ratio. Alright. Now, assuming that the wires have negligible resistance, calculate the equivalent resistance of all 60 bulbs. And because you see that they are all connected in parallel. Okay. So what's the good thing about parallel? When one light bulb is on, or one light bulb is maybe damaged, the rest can still light up. Okay, so this allows some patterns to be formed because now this is Christmas lighting. So we know that it is parallel. Okay, and because we know the power, the P and the V, and we have to use P equals to V squared over R, so we can find the resistance. Okay, so this is what we are finding, 12.5 ohm. And because they are now connected in parallel, right, so we have 60 of this. So this is the formula. If I want to find a parallel resistor, right, 1 over the resistor plus 1 over resistor, so on and so forth. Okay, and then we do an inverse. And now we have 60 of them, so it becomes 60 over 12.5. So the answer for the effective resistance on the secondary side is 0.208 ohm. Now, calculate the current in the primary coil of the transformer. So I'm supposed to find IP and state your assumption. Okay, we need to state that the transformer is 100% efficient so that we can apply our P equals to PS. Okay. But do we need to do that? Okay, because the light bulbs, they are all connected in parallel. Okay, so we have 60 light bulbs. Okay, and we know that the power of each light bulb is 2 watts. So the total power on the secondary side, assuming that all light bulbs are turned on, it will be 120 watts. And if we state that the transformer is 100% efficient, then that means the primary side, the power will also be at 120 watts. But PP is equal to IP and VP. Since we know VP, how much is VP? VP is 220 volts. So IP will be equal to 120 over 220, and we get this answer. Okay. Before I close, I must tell you all to really go and annotate, because even for me, sometimes I get lost. So I need to write down what is IPVP, PP, and so on and so forth. Okay, for the calculation part.